Hello, everyone. Hope you all can hear me fine. Uh, so I'm postdoc at ANU. I'll be talking about cosmic ray propagation in spatially intermittent magnetic fields. Uh, to give a brief introduction, cosmic rays are relativistically charged particles. They come in a huge range of energy, starting from few hundreds of MeVs to 10 to the power 11 GeV. They're detected directly, a lot of them, and also via indirect observational signatures like radio and gamma ray observations. And today I'm primarily talking about ultra energy cosmic rays, which are cosmic rays with energy greater than 10 to the power 9 GeV. And the source of ultra energy cosmic rays is really not a settled debate. It is whether it can be AGNs or supernovas, extreme supernova events or GRBs. It's not yet settled, but it's known to be extragalactic. To give you a number, the galactic cosmic rays, which are primarily responsible for radio synchrotron, are like 5G. So it's orders of magnitude less in energy. And this is more or less settled that they are accelerated in supernova shocks in the galaxies. Galactic magnetic fields, of course, these are charged particles, so they are affected by magnetic fields. And the galactic magnetic fields are of order of 5 microgauss roughly, but it's spatially intermittent, which is the topic of my talk today. And I'll discuss in much more detail as we go ahead. And ultra energy cosmic rays, if you calculate the Larmor radius, which is basically if you assume a constant field, the particle just doing helix around it, turns out to be huge. So it's not much deflected by magnetic field. It's like on kiloparsecs, 500 parsec to kiloparsec scales. But if the source of it was known, this ultra energy cosmic rays are very good probes to do cosmic ray astronomy. So, like radio astronomy, gamma ray astronomy, there is a cosmic ray astronomy could be used if the source was known. And the top question of the talk today is: can intermittent magnetic fields, this is the structure of magnetic field, aid cosmic ray astronomy, or can we find out something about the source of ultra energy cosmic rays? Now go. So this is I'm showing the spectrum of all cosmic rays. So this is like few GeVs. Most of particles are there. It ranges such a huge range of scales, orders of magnitude, and it's almost a very good power law. I would say this is the biggest power law in star. Uh, but there are few features, and it's well known that at very high energy, it's difficult to trap these particles within galaxies. So they are mostly extragalactic. The origin is certainly extragalactic, that much is bit settled at very high energies. And here I'm showing a plot for ultra energy cosmic rays. This EEV basically means some 10 to the power 10 EV, electron volts. And this is from the Auger collaboration. And the color you see is basically flux coming from different directions throughout from where we can see. And you can see there is a slight asymmetry. There's a dipole. It's been characterized as a dipole. And the name of the game is we see ultra energy cosmic coming from various directions. And if we correlate it with known sources, like if we know there is some GRB there is some AGN jet there is some FRB there, then we could correlate locations of it. And in those directions, we should see enhanced flux because if they are the source. But it seems like this is very flat in that sense. There is just a single dipole. This is a known galaxy distribution from there, and these are just different energies. So again, different energies travel differently. And one of the culprits in analysis of this is galactic magnetic fields. So this is the magnetic field structure from the Planck satellite. And what the color you see, the drapery pattern you see is like dust pollution. So basically like proxy for magnetic field directions. And you see it has such a rich structure. It's almost made by artists, I feel. So there are loops. The magnetic field in the southern plane is not, southern hemisphere is not really symmetric to northern hemisphere. In this, there is a lot of structure. And this structure is basically what is called spatial intermittency. So if on smaller scales, the things are spatially intermittent. Since I'll be using this word a lot, I'll spend a few minutes to describe what is intermittency in terms I am talking about it. It's also referred to as non-Gaussianity, not volume filling, filamentary. These are all terms to refer to very similar things. So to give you a simple example, if you take a 1D Gaussian distribution with mean 0 and standard deviation 0.5 or 1, you land up with such a series. If you think of a distribution which is very similar to this, but the second line, where you do have similar numbers, but once in a while, you have a huge peak So this is non-Gaussianity. It is also random. That doesn't remove the randomness of the thing. So this is still a random distribution, but just not Gaussian. To visualize it better, if you look at magnetic fields in some simulation, this is from one of my simulation, you have this snakes in the plane. So it's basically you have a very strong field, then there is very weak field in between. Again, you get a strong field, and this has this filamentary structure. It's still very much random. There is no uniform direction or shape of these filaments. But the snakes come at different places with strongness. So the question is, how does this strong, weak pattern affects the propagation of ultra energy cosmic rays? To be a bit more mathematical, if you do a PDF, if you do a histogram of this kind of field, it usually have this long, heavy tails. The Gaussian distribution, everything finishes by plus minus 3 sigma. But if you have such a non-Gaussian or spatially intermediate field, you have such heavy long tails. And the question we're asking today is, how does this kind of structure affect particle propagation? And the setup is very simple. This is just we simulate a small patch of ISM, small patch of galaxies, kiloparsec scale, around 2 to 5 or 0.5 kiloparsec scale. And we solve MHD equations to generate magnetic field. And what you see on the left-hand side is the solution of that MHD simulation. It has this, the color is magnetic field strength. It has this filamentary structure with extremely strong field in between, and then weak field around it. So this mimics that structure I was talking about. But now you need a test case, a comparison case. So for comparison, we also compare it with Gaussian fields. And how is this Gaussian field generated? We take the field from simulation, the intermittent field, take a Fourier transform, go to Fourier space, add random phases, take an inverse Fourier transform. That is the right-hand side. So by construction, the left and right-hand field has exactly same power spectrum, but they look so different. It is by construction. So the idea is the scale is same, power at each scale is same for both the fields. It's just the structure which is different. Of course, if you plot the power spectrum of these two fields, they sit on top of each other. This is just sanity check that they are exactly the same. But the histogram which I was talking of looks different. The non-Gaussian field has this heavy tails compared to Gaussian field, which ends in plus minus 3. So any 2 points, structure function, correlation function, power spectrum, everything is same for both of these fields. Now we have generated fields. So we put in particles. This is just textbook and V cross B written in some normalized form. So we take magnetic field from this turbulent simulation and his phase randomized Gaussian versions. We put a lot of particles. This is some just technical details. We use Boris scheme. And in this numerical simulation, there are a lot of decisions to be made. So this I'm just trying to explain how they made. So what should be a time step for Newtons? So here we know these are particles. What is the fastest particle? If you are resolving fastest particle, you are resolving everything. So there are some of these technical details. And the basic question is, if the ultra energy cosmic rays are entering our galaxies, and if they see a Gaussian field and a non-Gaussian field, do they feel any difference or not? This is particle trajectories. So they put bunch of particles in these boxes. On the left-hand side, when the energy is very low, it's diffusing. They're changing a lot. But at ultra high energies, you see they are traveling in a straight line paths with slight deflections. Of course, once in a while you'll deflect a lot because you'll hit this filament. So I have in previous work I have mostly looked at how the diffusion, which is of a 5 GeV particle from synchrotron perspective, changes if you have non-Gaussian fields. Today I'm talking about how does the non-Gaussian field affect the ultra high energy cosmic rays. So basically, we put bunch of particles and then look at how their deflection angle changes. So if it's traveling straight line to start with, once it enters the box, when it leaves it, how much the deflection angle has changed. And what I'm showing here is just a distribution of deflection angles for Gaussian and non-Gaussian magnetic fields. So the intermittent and random magnetic fields, the randomized versions. The dashed lines are for randomized version, and the solid lines are for intermittent magnetic fields. And it turns out overall there is a less deflection when you have intermittent magnetic fields. So they're better for cosmic ray astronomy. They're moving less away. Of once in a while, so you do see larger amounts of deflections, but they are less probable. So once in a while you hit this filament and then you deflect a lot. But that happens rarely. The most of the volume, it's not deflecting as much as it does in the Gaussian case. Of course, this, again, because we are putting a simulation, we assume some scale. So this is particularly for this 10 to the power 9 GeV. So it's extremely high energy part. And this is the explanation. So imagine cosmic ray getting in from this side. If you have a Gaussian field, it is deflecting more or less throughout. And if you have non-Gaussian field, it deflects only when it hits this filament, the probability of which is very rare. So there are it is deflecting more, but it is less frequent. And here it is deflecting less, but it is more frequent. And it turns out that the more deflection, not the amount, the times it deflects from its original trajectory is more important. So to sum up, magnetic field structure is important for cosmic ray propagation. It's not captured by power spectrum, as I showed you. You can construct fields which have exactly the same power spectrum and gives different results. There is less deflection by ultra-energy cosmic rays with intermittent structure, and is explained by less frequent and more extreme deflections. And the next plan is to include this in cosmological simulation, because I've already only factored in galactic field, but also there is IGN, which might make some changes. There are some references here. And I'll end with this request to all hosts of the institutes to join our ASA ECR symposium, and all ECRs to join our chapter. Thank you.
Thanks, very nice. It seems like the relationship between the length scale of your intermittent structure and like the longer radius or something would be very important here. I didn't get whether you were solving the full orbit or are you just doing the guiding center of the particles.
Yeah, so this is solving the full orbit. And this is this length, when I say low energy cosmic ray, this is the length scale of intermittent structures. Sorry, Larmor radius is less than the length scale of intermittent structures. So they are diffusing, they see a lot of they see the structure of the field, but at higher energies, they just wash it off.
I guess I was just fascinated by the fact you get just a dipole.
Yeah.
So like, even if you had like some effect from the galaxy, why would it be like this dominant dipole?
Yeah.
In the sky? Like, is that,
it's
not to say it's direction or something stupid. It's
no, I think it's unclear, and the people have tried various things. Like people have tried putting large scale field also. What I was showing is mostly small scale structure, but if you put large scale field also, it's difficult to explain this. It's 20% asymmetry in dipole. It's not clear yet.
What's the angle between that dipole and the CMB dipole?
I'll check. I have to check because it has. Sorry, I'm not aware of exact number. Doesn't count. But this is very close to ZZ case spectrum, the higher energies. But the CMB interaction happens at even much larger scales, the GZ case spectrum. So I think it should not match, but the number I'm not sure.